Tabular integration is a technique that can be used to help carry out integration by parts. In this set of videos, we'll go through what this method is, how you derive it and how it works, as well as some cautions as to when you might not want to use it for solving integration by parts problems. So integration by parts is a method that is used a lot for doing certain types of integrals, and tabular integration is a way to structure that method, make it look a little bit easier, seem easier to carry out, as well as get to answers more quickly in specific cases. The most common use case for this and the most useful version is when you're doing integration by parts and it must be done multiple times. As we'll see by the end, for like 1 or 2 steps, it's probably not worth this method, but beyond that, this method is fantastic for doing multiple rounds of integration by parts. It's also super useful when the function you are differentiating eventually goes to 0, namely if that function is a polynomial. Let's see what this method is and how we get to this process for doing integration by parts. Here we have our 2 main formulas you will see in a variety of textbooks for integration by parts. And really, since this is a different way of looking at integration by parts, it's going to come from the exact same formulas. So we have our 2 versions here. We have the U and dv version, which some books will use, as well as the version involving functions, f and g, here written with f times g prime as this initial integral, and then a gf prime as a second. The point being here, if u is f, you set dv to be g prime of x dx. These are the same formula. Now, for the sake of deriving the idea of tabular integration, I'm going to define some new notation here. This is not common notation, but it'll be useful in seeing how this process works here. The notation I want to use for this is that if I have a function f with a number up in parentheses, this will be the first derivative of f, or in general, if I place the 1 by an n, this will be the nth derivative of the function f. This one's pretty common notation and is used a lot. The other one is not, and I'm going to use the same notation but Roman numerals in the exponent. So a 1, for instance, to indicate repeated integration. This will be the first integral of g, or the first antiderivative of g. And we keep going. So for instance, if I put a 2 in Roman numerals, that is a second antiderivative, or taking integrals twice on the function g. And if I need a generic letter here, I'll use a capital N for the nth antiderivative of g. Should this be notation? I don't know, probably not, but it'll be useful here for seeing how we carry out this method and getting to a process for tabular integration. What does this process look like? Well, so let's start with an integral of just f of x times g of x dx. Now you'll notice this here is not the same as what I have up here. So up here I have f times g prime, which fits nicely into the formula of integration by parts. Here I just have f times g. And when you're looking at a problem, you'll probably just see f times g first and have to think about, okay, what can I integrate? How can I solve it out? So we're going to start this process at just f times g. And what I've seen most places for tabular integration is it starts with this here. Now I want to do integration by parts with this setup. Let's assume for the sake of this that I want to differentiate f and integrate g like it was g prime in the original formula. We have g instead. So if I write that out, what I have is that my u, integration by parts, I prefer the uv notation, so I'm going to use that for my examples here, is f of x, and my dv is g of x dx. Then my du, I differentiate the f, which gives me f prime dx, and for v, I want to integrate g. Well, now I have a notation for that. In an earlier class, we're in Calc 1, you may have seen this as a capital G, but for the sake of keeping things simple with notation, here's our new one here. This will be g upper 1 Roman numeral of x. And so integration by parts then tells me this equals uv f of x times g upper 1 of x minus the integral of v du. That's the integral of g1 of x, f prime of x, or for our notation, f1 of x with a Arabic numeral 1 in there, dx. This seems like a lot of notation here for nothing, and it kind of is. This is really only useful if I want to do this more and more and more times. So let's say we want to do integration by parts again on this integral that remains, this g upper I, f upper 1 dx. Now I could, with that, make a choice differentiating the function I want. The problem is if I choose to differentiate the g and integrate the f, I'll wind up right back where I started. Because I'll end up with the derivative of g upper 1, which is just g, the integral of f prime, which is just f, and everything cancels out and all goes away. So don't do that. We want to keep the same letter functions as our derivatives and our integrals. So we'll end up with then integral of f of x, g of x dx, our starting point, equals, keep our same first term here, and now we're going to do integration by parts on this other term here. So again, I'm going to call u as the f-based function, so f1 of x, and my dv will be the g-based function, so g upper 1 of x dx. We can differentiate integrate. My derivative here, du, is f second derivative of x dx. My integral of g is now g upper Roman numeral 2 of x. And I can do my integration by parts. Remember that I have this minus sign here that I'm carrying through, so I will see that minus sign and then uv minus integral of v du. G second integral, f second derivative dx. And if I distribute my minus sign, I will see this. I have my first term still, minus the second term, and the remaining integral, which has a plus sign because there's two minus signs involved. You can keep going with this process. What you see if you spot the pattern here is first alternating signs, right? When I do the next step, my uv function comes in positive because of the plus sign here. We have alternating signs. Every term here has an f and a g. You're consistently integrating g's and differentiating f's. In the normal terms, the g has one higher number than the f, right? It's g first integral times f normal, g second integral times f first derivative, and the integral one has the same number across. So if we spot all these patterns here, we can use this to build a method that'll get us to this point a lot faster without going through all the u and v and dv processes, because we know what the result's going to look like. It's always going to have these alternating signs, these f's and these g's, and how they're all structured. So let's get rid of all the u and v stuff and just get a method that gets us right to this answer right away. So what is this method here? Tabular integration basically says, let me just build a table that does all this work for me to work out the answer. So let's say we have this function. We're trying to integrate f of x times g of x dx just like before. What you do is make a table with two columns. You put f of x in the first column and g of x in the second. And what you're going to do is you're going to differentiate the f column. So I'll put a d up here to indicate that. This is a pretty common notation as well. And an I over the g, no integration. You're just going to go down this table and repeatedly differentiate f, repeatedly integrate the function g. Just like we saw, that's what you need for this process. If we fill that in, we'll have f first derivative, f second derivative, f third derivative, so on. And we'll have g first integral, g second integral, g third integral, and so on. So there's our differentiating f integrating g bit. Now I need the alternating signs, and to do that, I will just put them on the left side of this table with a plus sign in the first row, and then alternate down like that. Now, how do I write this antiderivative, this integral? Well, I'm going to start from the top, and for each one of these f terms, I'm going to pair it with the one down and to the right. So those two terms that I've done there with the purple give me f of x times g first integral of x, and then you keep stepping down row by row, always taking an f function and then the g thing that's down and to the right of it. So I'll have this f1, this g2 are paired together with this minus that's next to the f. So minus f first derivative, g second derivative of x. You can keep going. To show you get the same form as before, I'm going to do the wrap up part here, but you could continue further on. For the last row you want to do, you take one row straight across the table. So once you're done, if you want to then go to an integral step next and sort of wrap up the integration by parts process, you take a row straight across and end it there. So then you have your last step will be plus the integral, so now going straight across, it's an integral, f2 of x, g upper 2 of x dx. And if you compare this formula, this one here, besides the colors and the term orderings, the formulas are identical. We've used a sort of more direct method or a sort of stripped down method where I've removed all the extra notation to get to this point faster. And so that's really the method of tabular integration. It is, you set up this table with a d for differentiating and I for integrating. You add the plus and minuses down the side and you write out your answer like this. The key points are you make a d and I column. Every term that is not in the integral is the f, and then the g thing that's down to the right of it. And the minus signs go with the f. And the last line here is the horizontal across inside the integral. So let's do an example to show how this would work in an actual problem context. So I want to do the integral of x squared e to the 2x dx. So I want to differentiate the x squared, because that's going to eventually go away, which is great for this method, and integrate e to the 2x. I'm going to make my table here, d I, and I start with the d side with x squared, and the I side with e to the 2x. I'm going to differentiate x squared. X squared, I get 2x, I get 2, I get 0, and I know I can stop at 0 because everything else goes away. Integrating e to the 2x gives me a 1/2 e to the 2x, a 1/4 e to the 2x, a 1/8 e to the 2x, and I could keep going here, but I've now hit zeros on the left side. Whatever I write down here would get paired with the 0 and not matter anyway. We put in our plus minus signs, and then just write out our answer. So integral of x squared e to the 2x dx should be, first term is x squared and the 1/2 e to the 2x down and to the right. Second term is the minus 2x and the 1/4 e to the 2x over here. Third term is the 2 and the 1/8 e to the 2x. And then I have a term that is minus 0 times stuff, or in this case, minus, as an integral, 0. Integral of 0 is just a constant plus c. I can rewrite this bit to make things a little bit nicer and get an answer of the form 1/2 x squared e to the 2x minus x over 2 e to the 2x plus 1/4 e to the 2x plus c, or I guess factoring out the e to the 2x. That would be your answer for this problem. Now, for comparison, I'll work it out using normal integration by parts just to show you the difference. I'm not going to do that live, but here's what it would look like done via normal integration by parts. The answer we get here is the same, and that makes a lot of sense because it's still integration by parts what we're doing here. But we found a different way to express it and write it out to make it look a little easier to solve out this kind of problem. So it's up to you whether you want to use this method here, the normal way, or tabular integration. But in the problems like this, both methods work out well to solve out the problem, and that's what this is here for. Tabulation is a lot quicker when you go beyond just 2 steps, as we'll see in our future videos. But here's the idea of the method, how you structure it, and how it works for solving integration by parts problems.